Elon Musk is a man on a mission. Quite apart from his tricky day job, weaning mankind off gas-guzzling automobiles, he also plans to drag our civilization over to Mars. And he wants to do it soon. To this end, Musk has been frantically developing a pioneering interplanetary vessel known as Starship, launching and iterating fresh prototypes at a frankly insane rate. But how does it all work? And what's inside that giant shiny cylinder that keeps crashing? Today, we gingerly venture onto the long-suffering Boca Chica launchpad for a sneak peek inside the Starship. During a recent interview with podcast host Joe Rogan, Elon Musk offered a typically smirk-inducing glimpse into the thought processes behind his signature rocket. Musk told Rogan he'd watched screwball Sacha Baron Cohen comedy The Dictator, in which a tin-pot leader of a fictional nation orders his engineers to make a rocket pointier in order to strike fear into the hearts of his enemies. And actually, that's also what I said. The same thing, Musk told Rogan. You know, Starship. We need to make it more pointy, he apparently informed his SpaceX team. Rogan asked Musk, quite reasonably, if a pointy rocket is significantly more aerodynamic than a blunt one. Musk replied that the new design is arguably slightly worse. Still, everyone thought it would be funny if we made the rocket more pointy, so we did. Not only is Elon Musk's great hope for the future of mankind pointy, in the grand tradition of classic sci-fi rockets, but his 164-foot-high Starship is also notably shiny. Why? Because it's made of stainless steel. This is for a number of reasons, as Musk himself has helpfully explained elsewhere. It's obviously cheap, and it's obviously fast, he told Popular Mechanics. And fast, in terms of production, fits nicely with his vision of getting to Mars in the swiftest possible time. Expense is another factor. Carbon fiber, a more conventional rocket-building material, costs some $135 per kilogram. But around a third of carbon fiber ordered from the manufacturer needs to be scrapped when wastage is taken into account, after being cut to the precise size and shape needed to make a spaceship. So the true cost of carbon fiber is actually nearly $200 per kilogram, explained business whiz kid Elon Musk. Compare that to just $3 for stainless steel. Stainless steel also has a high melting point, an obvious advantage in rockets. Carbon fiber can only tolerate a steady-state operating temperature of around 300 degrees Fahrenheit, whereas steel can comfortably get up to and even beyond 1,500 degrees Fahrenheit without undue stress. This is thanks in large part to its shiny, mirror-like thermal reflectivity. And when you consider SpaceX's choice of fuel, cold liquid oxygen and methane, stainless steel offers the additional benefit of not turning brittle at ultra-low temperatures. Ever the tinkerer, Musk has looked into superior forms of stainless steel for use on his Starship prototypes. The present alloy used, known as 301 stainless steel, certainly has a good pedigree and has seen action in space for decades. But as he tweeted last year, we should be able to do better in the 2020s than they did in, like, the 50s, you know. So I think we'll start switching away from 301 maybe in the next month or two. He goes on, helpfully, to be rather more specific. Some parts will use 304L as it has higher toughness at cryotemps. 301 stainless steel alloy comprises a blend of nickel, chromium and iron and is more resistant to corrosion. 304 is similar, with a higher chromium content which makes it slightly less likely to corrode, and slightly higher performing when it comes to bearing heavy loads at high temperatures. The rings you see running up the side of Starship prototypes every 1.8 meters are an artifact of the fact it's constructed using stainless steel, 1.8 meters being the standard maximum roll height of commercial steel. So what's inside that steel tube? Up on top, in the nose cone, we find the payload compartment. On current prototypes, this is left more or less empty, but in time it will be fitted out into a multi-functioning cargo bay. Alternatively, depending on the application, and certainly only after they've got the hang of landing, crew quarters here could hold about 100 people comfortably on a trip to Mars. However, that number could be increased, reckons Musk. You could conceivably have 5 or 6 people per cabin if you really wanted to crowd people in, he recently mused. But I think mostly we would expect to see 2 or 3 people per cabin, and so nominally about 100 people per flight to Mars. This payload bay would also host common areas, storage space, and a shelter where folks could hide out in lined chambers from potentially cancer-causing freak solar storms. Right now, phone footage taken by Musk himself up in the nose cone shows a spherical device known as a header tank. More on the fuel situation shortly, but while we're up here, it's worth pointing out the Tesla battery packs attached to car engines adapted from a design used in Tesla's production Model 3. What are they doing up here? The overarching design philosophy of Starship puts a premium on reusability, which means ultimately this giant steel beast has to land at some point. But unlike its much leaner SpaceX Falcon cousin, which lands vertically almost as a matter of course nowadays, Starship is so huge it needs to do something altogether more ingenious. To bring Starship most of the way to the ground, flaps are extended from the side of the rocket. The idea is these use Earth's atmosphere to slow the descent. As Musk puts it, you're trying to create drag rather than lift. It's really the opposite of an aircraft. This approach to landing, or at least getting close enough that Starship engines need less fuel for the last leg, requires much less fuel and hence weight than the Falcon method. The Tesla batteries and engines up top operate the actuators that extend the flaps. Clever stuff. Further down the rocket, we come first to the liquid oxygen tank, then to the liquid methane tank. This fuel mixture, unconventional compared to more traditional rocket fuels, was chosen by SpaceX for several reasons. On balance, it's less dense and therefore less weighty than using hydrogen. It burns clean, which is crucial when you're hoping to reuse rocket engines time and again. Also, thanks to the discovery of ice on Mars, future missions can apply a bit of chemical wizardry known as the Sabatier process to generate methox fuel to spur on the homeward journey in situ on the red planet itself. These two giant tanks contain a whopping 1,200 tons of fuel, separated by a near-hemispherical bulkhead known as the Common Dome. This bulkhead is, in itself, a great SpaceX innovation. Conventionally, oxygen and fuel tanks are separated by two hemispherical domes, wasting precious space in the gaps between. Back to that sphere in the nose cone, which is one of two header tanks on board, the other sitting in the common dome we just mentioned at the interface of the oxygen and methane tanks. The nose cone header tank holds a separate supply of liquid oxygen, and the common dome header tank contains its own stash of liquid methane. These reserves are only brought online during the final stage of landing, once the main fuel supplies in the big tanks have been exhausted. In this way, Starship's thirsty Raptor engines can enjoy fresh, high-pressure methox when they most need it. This pressure is so crucial for their operation, Elon Musk specifically blamed inadequate fuel header tank pressure for the SN8 crash and burn back in December. This smart header tank workaround also protects the essential landing fuel reserves from so-called burn-off, which will be a significant problem on longer missions that are exposed to greater solar radiation. Their compact size also avoids the mechanical headache of what engineers evocatively refer to as sloshing. And the oxygen header tank's position in the nose cone is believed to offer a useful landing counterweight, on current prototypes anyway. The engines themselves are SpaceX's pride and joy Raptors, only 3 for now, optimized for operation at sea level. But later operational versions of Starship will likely have 6 Raptors, with the additional 3 optimized for vacuum conditions. The vacuum Raptors will have a larger nozzle diameter, 2.8 meters, compared to the dinkier 1.3 meter sea level version. As we write, Starship prototype SN10 is on the launchpad, loaded up with design refinements that will hopefully help it land safely after its test flight and move mankind one step closer to Elon Musk's ultimate dream of a future beyond our orbit. History is going to bifurcate along 2 directions, he told a conference earlier in the Starship program. One path is we stay on Earth forever, and then there will be some eventual extinction event. The alternative is to become a spacefaring civilization and a multi-planet species, which I hope you would agree is the right way to go. It's good to know somebody is on the case at least. What do you think? Is Elon Musk moving too fast to truly absorb the lessons of his Boca Chica adventures? Or is the challenge so urgent he might not even be iterating quickly enough? Let us know in the comments, and please hit subscribe for more upwardly mobile tech content.